Bismillahirrahmanirrahim. We are studying the course Category Theory. Let us recall few concepts from our previous session. Recall that we studied the category of sets and functions. We denoted this category by SET set. This is the category of sets and functions. And the structure of this category was, first of all, we have the collection of all the sets, the collection of all the sets. Secondly, for any two sets A and B, for any sets A and B, a collection which we denoted by Hom AB of all the functions from A to B. All the functions with domain A and codomain B. And thirdly, for each set A, a function with domain A and codomain A as well, called the identity function, denoted by this particular symbol. And the fourth component was for all sets A, B, and C, a function which is from Hom AB cross Hom BC to Hom AC, and it is given by FG, which is function from A to B, and G, which is function from B to C. This function goes to G circle F, which is in fact composition of F and G, G with F in fact, and this is, you know that this is function from A to C, and this is called composition. And the fifth component of our definition of this category set was that for all F belonging to for all functions F belonging to Hom AB, and G belonging to Hom BC, and H belonging to Hom CD, we have H composed with composition of G circle F is same thing as composition of H and G composed with F. This is in fact associativity of composition. That is, the composition of functions is associative. Is associative, and the sixth component of our definition was for all F belonging to home AB, it is better to write it in the form of arrow. So F is in fact a function with domain A and codomain B. So this is the function we are talking about, which belongs to home AB. So for all functions F belonging to home AB, if we compose identity function on B with this function F, result will be equal to F. And if we compose F with identity function on A, result will be F again. These two rules are very easy to see from this particular arrow, because identity function on A will be a function from A to A, and then you compose with this. And identity function on B will be function from B to B, and then you can compose it with F. So these are the conditions under which set, the collection of all the sets, is a category. So having said that, we proved two results, and these results were about monomorphism and epimorphism. In fact, we did not use these two phrases in our previous session. Let me write what we proved last time. So first result we discussed was a function f is onto, we proved in previous session that a function f is onto if and only if G circle F is equal to H circle F, implies that G is equal to H. That is, F is right cancelable. And we discussed this particular proposition in detail in our previous session. And we also proved that a function f is one-to-one, is one-to-one if and only if f circle G, f composed with G, is equal to F composed with H implies that G is equal to H. That is, F is left cancelable. And we noted that these two definitions, first definition of onto function and that second definition for one-to-one function, these definitions are free from use of elements of the sets. So this is the important thing to note about these two definitions. Now we come to few more examples of categories. So few more examples of categories. So let's consider this particular category GRP. We denote it by GRP. This is in fact the category of groups and group homomorphisms. The category of groups and group homomorphisms. So note that when we were discussing the category of sets, we had sets and functions between sets. Now we are going to discuss the category of groups. So this will be collection of groups, and for two groups, the group homomorphisms from first group to the second group. So in this category, we have collection of all the groups as we had in case of set, collection of all the sets. So in this case, we have collection of all the groups. Next, we have for all groups A and B, for all groups A and B, a collection we will represent with same symbol home AB, but in this case home AB will be the collection of all group homomorphisms from A to B. So a collection home AB of all group homomorphisms with domain A and codomain B are from A to B. So this is the second component. And thirdly, similarly as we had in case of sets, for each group A, a group homomorphism with domain A and codomain A as well, the same as it was in the case of category of sets, and we denote it by this particular symbol. But in this case, this is identity group homomorphism with domain A and codomain A. called identity group homomorphism. And the fourth component is for all groups A, B, and C, A, B, and C, a function from home AB. Home AB is the collection of all group homomorphisms from A to B. Cross home BC. Home BC is the collection of all group homomorphisms from B to C. So a function from this to home AC, and this function is defined as given F, which is a group homomorphism from A to B, and G, which is group homomorphism from B to C. To this particular ordered pair, we will assign G circle F, which is composition of these two group homomorphisms, and you know that G circle F is group homomorphism from A to C. So this is in fact composition of group homomorphisms. Let me just note that where G circle F is composition of group homomorphisms, F, which is from A to B, and G, which is from B to C. So composition of these two group homomorphisms. And we come to fifth component of this structure of this particular category, and that is going to be about associativity of composition of group homomorphism. So this is about associativity. Let me write it. It is about associativity. So for all, this same thing as we have done for the case of category of sets. So for F belonging to home AB, this means that F is a group homomorphism from group A to group B, and G belonging to home BC, this means G is a group homomorphism from domain B to codomain C, and H belonging to home CD. This means that H is a group homomorphism from group C to group D. So we for F, G, and H we have, if we compose H with composition G circle F, or we compose composition H circle G with F, these results are equal. That is, composition of group homomorphisms is associative. That is, composition of group homomorphisms is associatives. is associative. And the sixth condition, that is about composition with identity morphisms, and that says that for all group homomorphisms with domain A and codomain B, we have composition of identity on group A with function f with group homomorphism f is equal to group homomorphism f, and composition of group homomorphism f with sorry, I made a slight mistake here. In fact, this is going to be identity on group B. Let me draw the diagram. This was group homomorphism from A to B, and this is F. Now, this is identity from B to B. Identity from B to B. So, identity from B to B composed with F is equal to F. And this is identity from A to A. So this is F composed with identity. F composed with identity on A is equal to F. In fact, this diagram is very helpful for writing these conditions. So this was the last condition. So with these conditions, GRP is a category, the category of groups and group homomorphisms. We come to next example, and that is the category of rings. So it was first example, now we come to second example. Let's write it as RNG. This is the category of rings and ring homomorphisms. The category of rings and ring homomorphisms. So the conditions are same. First of all, we are going to consider collection of all the rings. First of all, collection of all rings. And secondly, for any two rings A and B, we are going to have collection of all ring homomorphisms with domain A and codomain B, which we will represent by hom A comma B. So for all rings A, B, a collection which we represent by hom AB, and which is in fact of all ring homomorphisms with domain A and codomain B. And then thirdly, for each ring A, we must have identity ring homomorphism from A to A. We denote it by same symbol, capital I and capital A as subscript. For each ring a ring homomorphism with domain A and codomain A as well, and this is identity ring homomorphism represented by this symbol called the identity ring homomorphism. And then at number 4 we are going to take 3 rings and we are going to ask for that particular function we asked in case of category of set and category of group as well. So for rings A, B and C, so for rings A, B and C, a function so for rings A, B and C, a function from home AB cross home BC to home AC. And as in previous cases, this function is defined as if F is a ring homomorphism from ring A to ring B and G is a ring homomorphism from ring B to ring C, this order pair will go to G circle F, which is composition of these two ring homomorphisms, and you can see that G circle F is a ring homomorphism from ring A to ring C. So we explain that where G circle F is composition of ring homomorphisms F and G. So this is composition of these two ring homomorphisms. And then at number 5, as in previous cases, we are going to say that composition of ring homomorphisms is associative. So this is associativity condition. So for F belonging to home AB, that is F is a ring homomorphism from ring A to ring B, and G belonging to home BC, and H belonging to home CD, we have, if we compose H with composition of G and F, or we compose composition of H and G with F, both results are equal. So this is what we call that composition of ring homomorphisms is associative. And the last condition is about identity ring homomorphisms, and that is for any f belonging to home AB where A and B are rings. So for any ring homomorphism with domain A and codomain B, if we compose identity morphism on ring B with F, result will be equal to F. And if we compose F with identity morphism on ring A, result will be F again. So these 6 conditions define the category of rings and ring homomorphisms. So we can have more examples. In fact, there are many examples. So let's take this particular example, and that is we denote it by C or NG. This means the category of commutative rings and ring homomorphisms. The category of commutative rings and ring homomorphism. And you can very easily see that what we are going to write in this case. First of all, as in previous cases, we have collection of all commutative rings. So first of all, we have collection of all commutative rings. And then, as we have done before, for two commutative rings A and B, Hom AB will be the collection of all ring homomorphisms from A to B. And same goes for identity ring homomorphism, composition of ring homomorphism, and their associativity and everything. So we do not go into detail now. You can write these things on your own. So other conditions are similar as for the category ring. Only collection of objects or collection of commutative rings we are going to consider in this case, while in previous case we considered collection of all the rings. So other conditions are similar as for the category or NG, which was category of rings and ring homomorphisms. Let's come to another example, and that is top. This is the category of topological spaces and continuous functions or continuous maps. So this is the category of topological spaces. The category of topological spaces and continuous functions or continuous maps. In this case, we are going to consider the collection of all topological spaces. So the collection of all topological spaces and other conditions for morphisms, for identity morphisms, for composition of continuous functions, you can write these conditions on your own as we have done for the category of sets, for the category of groups, for the category of rings. You can write all these conditions on your own. So you can write other conditions on your own. We can consider MON the category of monoids and monoid homomorphisms. So let's just write it. Mon. This is the category of monoids and monoid homomorphisms. So in this case, you will consider the collection of all monoids and then you will discuss the monoid homomorphisms just the same way as we have done for groups, for rings, for sets and so on. So you can write other details on your own. Even we have more categories. In fact, if you like, you can consider the category of left OR modules. We write it as OR mod. This is the category of left OR is on the left hand side. So the category of left OR modules. Of left OR modules and module homomorphisms. And even you can consider this category mod OR. We have written ring OR on the right hand side. So this will be the category of right OR modules. Category of right OR modules and module homomorphisms. Let me just note that in number 6 and number 7, the ring R is a ring with identity. Note that in OR mode and mod or in these two categories, or is a ring with identity. You know that when we say ring with identity, we means the ring has multiplicative identity in it. So R is a ring with identity. So category of left R modules, category of right R modules, and in both these categories, the homomorphism will be the module homomorphisms. So having discussed all these examples, now we are in a position to give formal definition of a category, and you can very easily see that what this definition is going to be. In case of category of sets, our first step was collection of all the sets. In case of category of groups, our first step was collection of all the groups. In case of category of rings, our first step was collection of all the rings. In case of category of commutative rings, our first step was collection of all the commutative rings. In case of category of topological spaces, our first step was collection of all the topological spaces. And then for each case, when we discussed category of sets, we discussed functions between sets. In case of category of groups, we considered group homomorphisms. In case of category of rings, we considered ring homomorphisms. In case of category of topological spaces, we considered continuous functions. In case of category of left R modules and category of right R modules, both we considered module homomorphisms. So with above examples in view, with above examples in view, we can now give formal definition of category. We can now give formal definition of category. And this is what the definition is going to be. Definition. Now we are going to denote category by a symbol, as in case of category of monoids we used this symbol MON. In case of category of left R modules we used this particular symbol. For category of right R modules we used this particular symbol. Now for definition of a category, for formal definition of a category, the symbol I am going to write, you will see that symbol, and if you do little practice you will be able to write it very easily. So a category denoted by, we will denote the category, formal category, general category, denoted by, we will write it as C, but C we write for set, for a set as well, and for set of complex number, field of complex numbers. And so we will make a little like this. This is not E, this is C. just a symbol we have designed on our own. If you like, you can make some other symbol, but anyway, I will write the category C with this particular symbol. So a category denoted by C consists of following data. Data is not very good word, but anyway, it is okay for us in mathematics. So consists of following data, and you can very easily see what we are going to say. In case of category of set, at number 1, we wrote collection of all the sets. And in case of general category, we will write collection of objects. Collection of objects. For example, if we are discussing the category of sets, then objects are sets. If we are discussing the category of groups, objects are groups. If we are discussing the category of topological spaces, objects are topological spaces. If we are discussing the category of monoids, objects are monoids. So first of all, we have collection of objects, and we will denote it by collection of objects denoted by object and then C. So objects of C. This is collection of objects, and this is the symbol for that. And secondly, for objects A, B of C, or for any objects A and B of this category C, collection of morphisms. A collection of morphisms and we will denote this collection by same symbol as we have already done, and that is hom AB. That is morphisms from A to B. Collection of morphisms hom AB, which are, we call morphisms arrows or maps, which are arrows or maps. We use these two words as well for morphism. So which are arrows or maps from A to B. From A to B. And then thirdly, and you know what we are going to say now, for each object A of C, a morphism, identity morphism from A to A. So for each object A of C, for each object A of C, a morphism and you know that we are going to write this morphism as I and a subscript A. So this will be a morphism which will belong to home AA. And this is called identity morphism, called the identity morphism. And then after identity morphism, we come to number 4, and that is about composition of morphisms. So for objects A, B, and C of category C, remember that? We are using C for object and C for category. For this reason, we are simply using this particular extension on C so that we can recognize that this is category and this is object of the category. So for objects A, B, C of C, we have a function. And you know that what this function is going to be. This function is going to be from home AB cross home BC to home AC. And what we are going to do is that if F is a morphism from A to B and G is a morphism from B to C, then this order pair is going to be assigned with G circle F, which is composition of these two morphisms, and that is morphism from A to C. And then our fifth condition is about associativity of composition. So associativity of composition. So for F belonging to AB, for F belonging to home AB, F is a morphism from A to B, where A and B are objects of the category C. So for F belonging to home AB, G belonging to home BC, and H belonging to home CD, we have H composed with composition of G and F is same thing as composition of H and G composed with F. So this is associativity of composition. So let's write it, that is composition is associative. So this was the fifth condition, and you know the sixth condition, that is about identity morphisms. and that is for any f belonging to home AB, for any f belonging to home AB, identity of B composed with F is equal to F, and F composed with identity of A is equal to F again. So we have generalized the conditions we have discussed in our examples of categories. So this was the formal definition of a category. Let me repeat it. In a category, first of all, we have collection of objects. Secondly, for any two objects A and B, we have collection of all the morphisms with domain A and codomain B. And thirdly, if we are given morphisms from A to B and then B to C, we can compose these two morphisms. And then fourthly, composition of morphisms is associative. And then for each object A, we have a morphism with domain A and codomain A, which is called the identity morphism. And then if we compose identity morphism with some other morphism, if composition is valid, then result is the morphism with which identity morphism is being composed. So these are the conditions, or these are the components of definition of a category. Now we see few more examples. So few more examples. So first of all, we have already discussed the category of commutative rings with the objects commutative rings, and morphisms are ring homomorphisms. We can consider a category whose objects are all the abelian groups, and morphisms are group homomorphisms. We denote this category by AB, capital A, capital B. This is from abelian. So for this category, objects are abelian groups and arrows. We call morphisms arrows, maps, and arrows are group homomorphisms. With all the other conditions, identity, group homomorphism, then composition of morphism, associativity of composition, all those things. We have another example, and that is, we can consider the category of vector spaces as well. Let's write it as VECT. VECT. In this case, objects are vector spaces over some field. Objects are vector spaces and the morphisms are, or the arrows are, you know that between two vector spaces we have linear transformations or linear maps. So arrows are linear maps. And then we can have another example. We can discuss category of metric spaces. That's little complicated, but anyway we can do that at some later stage. Zero is a category. Zero, this is a category which is empty category, which has no objects, no arrows. So this is empty category. This is empty category with no objects and no arrows, or no morphisms and no arrows. So we can have another category. Let's denote this category by 1. So this is a category. This is a category with one object and one identity arrow. This is a category with one object. This category has only one object, so there must be at least one arrow from that object to itself. So this is a category with one object and one identity arrow. Let's denote object by star. One object and one identity arrow. Identity arrow from star to star. And as we have done in our previous examples, we can denote it by this particular symbol. So this is a category again. You can check it. It satisfies all the conditions of categories. We can, if we are given any set, in fact, it is easy to see if this set is non-empty. So let S be a non-empty set. Non-empty, it is easy to see if this is non-empty. So let S be a non-empty set. So let S be a non-empty set, then S is a category. Then S is a category whose objects are the elements of the set. Whose objects are the elements of S. So objects are the elements of the set S and has only one identity arrow, and has only identity arrows in fact. So whose objects are the elements of S and has only identity arrows. This means that if A is an element of S, then there is an arrow from A to A, the identity arrow. That's it. So far, any set S is a category whose objects are the elements of the set, and arrows are the identity arrows only. So, having discussed this particular category, we come to a category which is very important category, in fact, in study of category theory, and that is the category of pre-ordered set. Before we discuss this particular category, let's recall what is a pre-ordered set. So let me say that we know that you might have studied it at some stage. We know that a pre-ordered set is a set P equipped with a relation we mostly denote it by this particular symbol. You must be very familiar with this symbol, and conditions are such that first condition is such that for all elements A, B, C belonging to this particular set P, the first condition is the condition you very well know. This is called a reflexivity. Reflexive property. Let's call it reflexive property or reflexive property. That means that every element A is related with itself. A is related with A, reflexive property. And secondly, that is transitive property. And that says that if A is related with B and B is related with C, then A is related with C. So these are the two conditions for P to be a pre-ordered set. If you include third condition, which is called anti-symmetricity, then it will become a partially ordered set. But anyway, as far as we are concerned at this stage, pre-ordered set will be sufficient for us. So if you want to see example, for any set X, the power set is a pre-ordered set. For any set X, the power set Px is pre-ordered set. Is pre-ordered set where the relation is given by being subset. Is pre-ordered set with this given by this relation inclusion. In fact, Px is a partially ordered set, but we know that every partially ordered set is a pre-ordered set, because if you include the condition of anti-symmetricity to the definition of pre-ordered set, it will become partially ordered set. And if from partially ordered set you drop this condition of anti-symmetricity, you can call it pre-ordered set. So every partially ordered set is a pre-ordered set. So power set Px is a pre-ordered set. So let's come to our structure of category we wanted to discuss. Now we come to the structure of category defined on P, this which is a pre-ordered set. Pre-ordered set. How does it becomes a category? Let's discuss that. First of all, we need to see what the objects are. So first of all, to see that what the objects are, objects of this particular category are elements of the set P. So objects are elements of P. So these are the objects. Secondly, we have to discuss that if we are given two objects or two elements of P, what home is going to be. So let's see that. For AB belonging to P, for AB belonging to P, that is AB are objects of this category, we have home AB, that is collection of morphisms from A to B. So this is equal to, now note it very carefully, home AB will contain one element if A is contained in B, and if A is not contained in B, in that case home AB is empty. So home AB will contain one element, will contain what that element is going to be. I will write it very soon. So home AB contains, we have to write an element here. So home AB contains one element if A is contained in, if A is related with B. Let me contain, we use it for this particular symbol, and this is, we will use related. So if A is related with B, then home AB will contain one morphism. So this is our definition in fact. And if A is not contained in B, or we can say that otherwise means if A is not contained in B, so otherwise home AB will be empty. There will be no morphism in it. Now let's see what symbol we are going to use here. There is only one morphism if A is contained in B. Let me repeat it. There is only one morphism if A is related with B. If A is related with B, then there is only one morphism. and we are going to write that morphism by this symbol. Different books use different notation for representing this particular morphism, but I think it will be slightly convenient to write it in this way. So this is a morphism from A to B if A is related with B. This is the symbol for that morphism. So if A is related with B, then this is the morphism from A to B, from A to B. So this is a very convenient notation. So this is the way we define home sets. So having defined home AB, next we come to our third condition for a category, and that is the identity morphism. So for each A belonging to P, A belong to P means A is an object of this category we are discussing. The identity arrow or the identity morphism. So the identity arrow, this will be written in this way. Identity arrow from domain A to codomain A. Identity arrow has same domain and codomain. So the identity arrow, this particular identity arrow is given by now this is an arrow if, let me recall what we were saying. This is an arrow if A is related with B. If A is related with B, then this is an arrow. And if A is not related with B, then this is empty. There is no arrow then in that case. So for identity arrow, note that our reflexive property says that for any element A belonging to P, A is related with A. A is related with A.